The energy released by the sun through the nuclear fusion reaction of hydrogen is truly enormous. It has the same power as 70 trillion atomic bombs dropped on Japan in the past, exploding every second. 1 kilowatt of solar energy hits an area of 1 square meter on Earth. If that energy can be converted into 100% electric energy, it is equivalent to the amount of energy that can fully charge an electric vehicle in 1 hour with solar energy received by an area of about 8 m in width and length. Efforts to reduce the carbon dioxide footprint by converting limitless solar energy into electricity have been widely carried out around the world in the last decade. However, with the exception of some areas such as deserts with a lot of sunlight, the actual production does not meet expectations compared to the installed scale of solar power. At night, solar power stops generating electricity, so an alternative power source that can replace solar power in the evening is essential for stable power generation. In the case of Korea, on average, only 2.5 hours out of 24 hours a day can generate electricity using solar cell. So the average annual utilization rate is only about 10%. Also, if cloudy weather continues for a long time, solar power becomes almost unusable, so in that sense it is a very unstable power source. In order to overcome these disadvantages of solar power generation, a method of installing a solar panel in outer space and transmitting the electricity produced there 24 hours a day, 365 days a year to the Earth using a microwave or laser has recently been developed in the United States, United Kingdom, China, and Japan. And the target time for commercialization is 2050, about 30 years from now. How realistic is this approach? Is it just something out of science fiction? I don't think so. Why? Today, Tech Trip will tell you about it. Let's start the Tech Trip. A method to install a solar panel in outer space and transmit the electricity generated thereto to the Earth using microwave as a method to solve the shortcomings of solar power that is inevitably affected by the weather and the rotation of the Earth first appeared in a 1971 patent. NASA also studied the method, but research was stopped in the 1980s due to the huge cost required to install solar power in space and the lack of a specific method that could actually transmit energy. However, the recent efforts to reduce carbon footprint in response to global warming and the emergence of reusable commercial rockets have sparked interest in space-based solar power generation, that is, SBSP. From now on, space-based solar power will be abbreviated as SBSP. SBSP consists of a solar cell that converts sunlight into electric energy, a device that converts harvested electricity into microwave and transmits it to the Earth, and an antenna that receives energy transmitted from space to the Earth. Devices installed in space are assembled after transporting parts to a low Earth orbit at an altitude of 400 to 900 kilometers using rockets. After assembly, SBSP is moved to a geostationary orbit about 36,000 kilometers from the Earth by means of a transport rocket. In geostationary orbit, SBSP rotates at the same speed as the Earth's rotation and is located far away from the Earth, so the Earth only blocks the sunlight for about 70 minutes. Therefore, it is possible to generate electricity by receiving sunlight for about 23 hours out of 24 hours a day. However, the biggest obstacle to practical application of SBSP is the cost required to launch the solar power system into space. The solar panel alone weighs 20,000 tons, equivalent to 1 gigawatt, equivalent to the output of one nuclear power plant. Now, if you use the retired space shuttle to send solar panels into space, it costs $19,800 to transport 1 kilogram of weight, so the transportation cost of 20,000 tons requires $200 billion. Although carbon neutrality is an important issue, compared to the cost of installing a 1 gigawatt-class nuclear power plant of $6 billion, SBSP is like failing the preliminary round. However, with the recent commercialization of reusable rockets, the cost of transportation to Earth orbit has been reduced to 1/10 of what it used to be. This means that the shipping cost of 1 kilogram is about $1,900 per kilogram. Therefore, the transportation cost of 20,000 tons of solar panels is reduced to $20 billion. However, it is still expensive and not at all practical. The method to solve this problem is to reduce the weight of the solar panel, and the most realistic method is to use a Group 3-5 solar cell with a structure similar to an LED instead of a silicon-based solar cell, that is, a gallium arsenide-type solar cell. Group 3-5 solar cells have a high efficiency of 40%, which is twice as efficient as silicon-based solar cells, and can be made into an ultra-thin film in a flexible form, which can significantly reduce the weight. A Group 3-5 solar panel weighing 1 kilogram has a power generation capacity of 5 kilowatts. As a result, if only the weight of the panel is considered, a 1,000 ton of Group 3-5 solar cell represents a power generation capacity equivalent to 5 gigawatt, so transportation costs can be significantly reduced. Of course, the problem is that Group 3-5 solar cells are at least 200 times more expensive than silicon-based solar cells, which are the most widely used on the planet, because of their complex structure and expensive production equipment. However, Group 3-5 solar cells have the characteristic of being able to maintain stability even when generating electricity by concentrating the sunlight received on an area that is 500 times its own area. Therefore, if you use a super-large reflector array made of a polymer reflective film to focus sunlight and then shine it on a Group 3-5 solar cell to generate electricity, the price will not be a big problem either. The solar cells currently used in the space station have an output of 160 kilowatts, so if about 6,000 such solar cells are installed, they will have a power generation capacity equivalent to the output of one nuclear power plant. And if the above-mentioned super-large reflector is used and Group 3-5 solar cells are used, the number of solar cells required can theoretically be reduced to 1/100th or less. Therefore, it can be said that it is not an unrealistic imagination at all. Despite the various solutions related to these solar panels, there are still a lot of problems. For efficient energy transmission, the size of the transmitting antenna installed in space exceeds 1 kilometer in diameter, and the size of the receiving antenna on the ground that receives the energy requires an enormous size exceeding 10 kilometers in diameter. One alternative that is being developed for miniaturization of energy transmission devices is the use of lasers. Transmitting antennas over 1 kilometer can be replaced by using multiple lasers with a diameter of about 2 meters, and when using the Falcon 9 rocket, it has the weight and volume that can be loaded at once, so the price can also be dramatically reduced. Recently, China has advanced its goal of launching an experimental SBSP into low orbit in 2030 by 2 years to 2028, and announced a plan to send tens of kilowatts of SBSP to geostationary orbit 36,000 kilometers away in 2030. I think that more than half of those who have watched this video up to this point still have doubts about the practical use of SBSP. However, it should be noted that there are two important facts. First, since SBSP's commercialization goal is 30 years from now, in 2050, more technological breakthroughs will appear in the meantime. Second, in addition to solar power generation, which is the main purpose of developing SBSP, efforts are being made to weaponize it. Perhaps the rush to develop SBSP again has something to do with the advent of a new Cold War era. Let's end today's video by watching a scene from a James Bond movie, Die Another Day.